Example 2, evaluating an integral as a limit of Riemann sums, part B. We want to evaluate the integral from 0 to 3 of x cubed minus 6x dx. Okay, so with n subintervals, okay, since we know that we have n subintervals, okay, remember that delta x is equal to b minus a over n. And since we don't know what n is, we do know what b is, we know what a is, and so therefore this is going to give us 3 over n for delta x. Okay, and then we also know that the initial value x subscript 0 is going to equal 0, and x subscript 1, okay, recall that we know that x subscript I is going to equal x subscript 0 plus I times delta x. So this becomes 0 plus I, which is 1, times delta x, which is 3 over n. So we have 3 over n. Okay, and then if we wanted to find x subscript 2, well, this would be 0 plus 2 times 3 over n, which is then equal to 6 over n. And then x subscript 3 would equal 0 plus 3 times 3 over n, which is equal to 9 over n. Okay, so in general, x subscript I is going to equal 3 times whatever the value of I is over n. Because what that means is 3 times 2 gives us 6 over n. 3 times 3 gives us 9 over n. Okay, so now we know what delta x is. Okay, and so now what we want to do is we want to then be able to then determine this limit. Okay, so we're going to take this integral that goes from 0 to 3 of x cubed minus 6x times dx, okay, and then we're going to write this in terms of a limit as n approaches infinity of the summation of I is equal to 1 to n of f of x subscript I times delta x. Okay, and so what does that equal? Well, then that equals the limit as n approaches infinity of the summation of I is equal to 1 to n of f. Well, we know that x subscript I is equal to 3i over n. So therefore we have f of 3i over n times delta x, and we know that delta x is 3 over n. Okay, and so now what can we do? Well, now what we can do is we're now going to be able to factor out the constant. So the constant is 3 over n. So if we look at the constant here, 3 over n, we can factor that out of the limit. So this is going to be the limit as n approaches infinity of 3 over n times the summation as I is equal to 1 to n. Okay, and we know that x represents 3i over n. So that means that we're going to plug that into our function. So we have x cubed, but instead of it being x, it's going to be 3i over n, and that's cubed, minus 6 times 3I over n. Okay? And so now, let's go ahead and then simplify this. So we have the limit as n approaches infinity of 3n times the summation of I is equal to 1 to n. Okay, so if we cubed 3I over n, well, 3 cubed is going to be 27I cubed over n cubed. And then minus, this is going to be 18 over n I. Okay, and so now, since we have subtraction, we can distribute this summation to both of those. So now what we can do is we can rewrite this now as the limit as n approaches infinity. Okay, and so we have 3 over n with the summation of I is equal to 1 of n of 27 I cubed over n cubed. And then minus, again, another summation, 3 over n of I is equal to 1 to n of 18 over n I. Okay? And so now what we want to do is now we can factor out this 27 over n and then multiply it by the 3n. And the same thing over here, we can take our 18 over n and multiply it by the minus 3 over n. So now we get the limit as n approaches infinity of 3 times 27, which is going to give us 81. And then n times n cubed is going to be n to the 4th times the summation of I is equal to 1 to n of I cubed. And then minus 3 times 18 is going to give us 54 over n squared times the summation of I, where I is equal to 1 to n. Okay, so why do we do this? Well, we want to use the definitions that we've seen at the beginning of the section here. Okay, so recall, okay, now up here we factored out the 3n. So the 3n, we used definition number 9 because we were able to factor out the value of c, meaning the constant. And the constant represented the value of c. So we were able to bring c outside of the summation, and therefore that represented c. Okay, now if we take a look at 5 and 7, well, we know that when we get the summation of I, we know it's going to be n times n plus 1 over 2. And we know that when we get the summation of I cubed, we know it's going to be n times n plus 1 over 2 squared. So what does that mean here? Well, that means that now this becomes the limit as n approaches infinity of 81 over n to the 4th, and now we know that this is what I cubed represents, or the summation of that I cubed. So that's going to be times n times n plus 1 over 2 squared minus 54 over n squared times this summation, which is going to be n times n plus 1 over 2. Okay? Okay, now let's multiply this out. So if we have the limit as n approaches infinity of 81 over n to the 4th Okay, this is n times n plus 1. If we distribute the n, then it means we're going to get n squared plus n. And when we distribute that and square it, so that means that here, this n times n plus 1 gives us n squared plus n, and then we need to square that. When we square that, we end up getting the following. We get n to the fourth plus 2n cubed plus n squared over that 2 squared, which is going to give us 4. And then minus, we have 54 over n squared times n squared plus n over 2. Okay, so now let's just reorganize our numbers. So we have the limit as n approaches infinity of, we got 81 over 4, okay, times, well, we know that we have n to the fourth plus 2n cubed plus n squared over n to the fourth minus, this becomes 54 over 2 times n squared plus n over 2. Excuse me, over n squared. Okay, so now if we simplify this a little further, we have the limit as n approaches infinity. And so we have 81 over 4 times, well, this is n over 4 over n over 4, which is 1, plus this is 2n cubed over n to the fourth, so that's plus 2 over n, and then that's plus 1 over n squared, okay, minus 54 over 2, which gives us 27, times, we have n squared over n squared, which is 1, plus 1 over n. Okay, so now let's go ahead and evaluate this limit. So when we evaluate the limit, we have 81 over 4, and the limit as n approaches infinity is going to give us 1 plus 2 over infinity, which is 0, plus 1 over infinity, which is 0, minus 27 times 1 plus 1 over infinity, which is going to give us 0. So technically this is 81 over 4 times 1 minus 27 times 1, which is 27. Which we therefore get the following. We get 81 over 4 minus, we have 4, and this is 108, so we get negative 27 over 4, which equals negative 6.75. Now let's take a look at this figure here. If we take a look at the figure here, this integral can be interpreted as an area. Can't be interpreted as an area because f takes on both positive and negative values. But it can be interpreted as the difference of areas where we have a1 minus a2, where a1 and a2 are shown in the figure above. So when we take this integral, we would say a1 minus a2 is going to give us negative 6.75. Now, if we wanted to expand further on this example, then we would look at the following. The figure below, okay, here, illustrates the calculation by showing the positive and negative terms in the right Riemann sum R subscript n for when n is equal to 40. The values in the table show the Riemann sums approaching the exact value of the integral, which is negative 6.75, as n is approaching infinity. So as n is going from 40 to 100, 500, 1,000 to 5,000, you can see that it's approaching negative 6.75. And therefore, this represents an example of that. And here, by taking the limit and using that information, we end up getting negative 6.75. And so when we get to the next section, 5.3, we'll see a much simpler method to be able to do this.